Hello everybody. Now we will discuss the materials model, which is very important in stress analysis of welding processes as well as the stress analysis in other manufacturing processes or maybe in metal forming process also. So, materials model is very important. It simply indicates that the relation between the stress and strain, and that actually always this relationship come looking into the this actual experimental data. We normally compare the actual experimental data with the theoretical values of the equivalent stress. If we assume that experiment can be done in a uniaxial tensile testing or some other condition, or other conditions mean the different strain rate at different temperature also. At the same time, that similar this single values of the stress, which is represented by the we have already shown that von Mises Ilk functional form, there we can represent the equivalent stress value. So, always the equivalent stress value and or equivalent strain value we can compare with this thing, and based on that different relationship may happen with the different parameters. For example, in materials model, purely empirical models, and that based on primarily purely on the empirical testing and the curve fitting, that we have saved so many test data at the different temperature value or different strain rate value, and we fit the curve and use that data. Then we express some formation. For example, in this case is the Holloman type of equation, Ludwig-Holloman equation. You can see also this equation is a kind of empirical constant, that empirical relation. The stress is related to strain with the n is the strain hardening coefficient and k is the some constant value. So, k can vary depending upon the material also. So, that means this kind of relationship always require to input to the model also, and if we want to develop some plasticity model during the deformation process. Similarly, the its materials model can be also semi empirical in nature. In this cases, combining the experimental as well as the physical phenomena has to be considered, and based on that we can reach some kind of the expression. For example, one of the other example is that Johnson-Cook model also. In this case, we relate the stress, but its stress is related to the strain and then strain rate as well as the temperature, and there may be some critical value also, then say applicability in the sense that within certain range of the temperature, certain range of the strain rate, this relationship may be applicable. So, this kind of the relation, to find out all this relation, it needs a lots of experiments, and if the data is compared or fitted purely based on the experiment, that is called the purely empirical models. Or sometimes we consider some micromechanics available or during the deformation process also, and in that cases some semi empirical models can be developed. So, both is finally linking the stress and strain, and that is useful to develop the model. So, but in this case, this materials model we need have lots of for example, if you use the Holloman type of equation, in this case we know that k and n are the unknown parameter, but in this case there are so many constant involved, and then maybe some limit involved, and as well as the parameter also. This not only the stress strain, rather temperature dependency also there, as well as the strain rate dependency is also there. So, therefore, this complex formula or that relationship between the stress and strain is required, and as a function of the other parameters when you try to develop some kind of the stress analysis model. That is the importance of the materials model in the stress analysis. Now, in general mechanical model in fusion welding process, we normally consider the static force equilibrium. In terms of the stress tensor, the equation can be expressed like that. That means, if there is some force acting, the force can be body force or some external force, such the internal stress will be generated and it make the balance and the under static equilibrium condition. That is the following in case of the stress analysis model. Now, in this case Pj is the body force and sigma ij is the stress tensor. So, that means sigma ij stress tensor mean in this case the within the internal stress will be, there may be some 6 or 9 components of the internal stress within this body. Now, apart from this thing static equilibrium equation, it is also necessary to consider the boundary condition. So, boundary condition can be like the displacement constant or concentrated or distributed load also. In case of welding problem, normally we consider displacement constant, in the sense that we restrict the displacement of a certain part. For example, suppose this is the solution geometry, and in an actual welding process, once do the welding process, we just clamping the other parts. So, which point the clamping is done, we can put some mechanical constant condition in terms of the displacement. For example, in certain direction the displacement can be 0, and in that sense we put the displacement constant, and that acts as a boundary interaction in the stress analysis model along with this force equilibrium equation. But in welding process the body force can be considered only for the due to the temperature from the thermal analysis. So, that means the body force Pij in this case is the it can be comes from the temperature distribution. We can consider this as a thermal load, that means because of the non-uniform temperature distribution within this body. So, that can act as a body force here and that will generate the stress value, and then this stress we are considering that material follow the elastoplastic law, that means this stress generation may cross the last yield point and comes to the part of the plastic domain. So, therefore, once it entered the plastic domain, then we have to consider the elastoplastic analysis. So, that is why we can consider any kind of the mechanical thermomechanical model in fusion welding process. But in this case we understand that normally we use the rate independent plasticity, the most simplified plasticity law. It will be useful in, for example, you can use the von Mises condition also, or in sulfurous process followed by the von Mises criteria. The associated flow rule also we have already explained, and bilinear isotopic hardening behavior. Bilinear isotopic hardening behavior means that we represent the stress strain diagram this way also, these two bilinear curve, and this is the stress strain diagram, and we represent this one is this elastic part and this is the plastic part, another linear curve. So, that is called the bilinear, and hardening rule we can consider the isotopic hardening. So, that means the isotopic hardening means the yield point is the initial yield point, this yield point evolves depending upon this thing. This is the second, third yield point reaching, but this changing of the yield point it depends on the strain hardening behavior of this particular material. So, that is why we consider this as a isotopic hardening, that means same center point of this yield surface or yield curve that is evolved depending upon the strain hardening phenomena. Now, it is also necessary in stress analysis model that relation between the strain and displacement, because if you remember on the very first when you develop some kind of the elemental form or basic fundamentals of the finite element applicable to the stress analysis in general, we normally form the stiffness matrix, but stiffness matrix is associated with the displacement, and we solve for the displacement field. Once we get the displacement field, from that displacement field we further calculate what is the strain value, and then after we calculate the stress value also. So, therefore, relationship between the stress and strain is required. So, in this case the small displacement theory if we follow, then strain can be is the U is the displacement field, del U by del x is equal to the strain along x axis, the epsilon y, the strain along y axis is the del phi by del y. Similarly, epsilon z del w by del z. So, this way we relate the between strain and displacement, and u v w here represent that displacement, and epsilon x y z refers to the normal strain component in x y and z direction, and apart from that the gamma x y y z z x that represents the shear strain component in the x y y z and z x plane respectively. So, therefore, the shear strain component can be linked with the displacement field equal to this part del u by del y plus del v by del x, that is the gamma x y, gamma y z is del v by del z and del w by del y. Similarly, x y equal del w by del x del u by del z. So, this way we relate all the shear strain and normal strain component in terms of the displacement field. It means that if it is to get the solution from the stiffness forming the stiffness matrix, if we solve for the displacement field in a stress analysis model in general, then once we get the displacement field, then we can update what is the strain field, or increment of the stress can be calculated. Now, in these cases assuming the isotopic material, so material properties are same in all three directions and thermal strain remains same in all three directions, and the incremental of the total strain, that means thermal strain, if isotopic material thermal strain remain in all three directions. So, we need to calculate the thermal strain also. In this case this represents the thermal strain component, and then total strain we can see is the simply summation of the thermal strain, plastic strain and the elastic strain. Already we have already mentioned that we normally do the stress analysis in the incremental mode. So, therefore, it is very important in the particular during the deformation process what is the increment of the strain. Now, total increment of the strain can consist of all this in case of elastoplastic analysis. So, total strain having this thing. So, the plastic component and elastic component will be there, because metal behaves like the elastoplastic material, and apart from that there is a application of the temperature or non-uniform temperature distribution that induce the thermal strain. So, therefore, this way we can say the thermomechanical analysis, then all the strain component has to be considered. Now, based on the increment of the strain, we can put this, we can form the incremental form, what is the increment of the stress in a particular time step or in a particular load step. But before that, this displacement field relation already have explained that epsilon I j equal to half of del u I by del x j and del u j by del x I. So, that is we have already explained what are the normal strain and the shear strain component, but in these cases we assume the small displacement theory. If it is a large displacement theory, then this accounts the small displacement component part, but if variation of the or higher order differentiation of the displacement field, then we can consider the large displacement field, and in these cases this component extra component accounts the large displacement or the variation of the displacement in the small zone. So, that sometimes it is possible to predict the what is the buckling happening inside the very thin plate. So, in that cases maybe it is necessary to consider the large displacement theory. And apart from that thing, it is also necessary to understand this stress analysis model, that average or equivalent stress. Average or equivalent stress, we can see that always when you apply the von Mises yield condition, we always estimate the what is the value of the principal stress component, and from the, if you know the principal stress component sigma 1, sigma 2 and sigma 3. So, using this we say this is the one single component, the average or equivalent stress component, which consists of the all the principal stress component. So, this average value or equivalent value consisting of the all theoretical prediction of the principal stress components, and this average value always we compare with respect to the experimentally measure the stress value one particular strain component. That is why we need to know the materials model also to relate between the stress and strain, and then theoretically once we calculate what is the equivalent value of the stress by following some kind of the plasticity, for example following in this cases following the von Mises yield function, then we estimate the average stress value, and this stress value always has to be compared with respect to the experimental value, but experimental value we normally obtain from the uniaxial tensile testing. So, from the uniaxial tensile data we compare, and accordingly we can decide the different strategy or putting the flag, and in case of the stress analysis model. So, analysis of the stress and strain in welding in general procedure is that first is the temperature history. Definitely once we go for the stress analysis model, we need to do first the thermal analysis. That means we need to know the information of the temperature data. So, then temperature history obtained from the thermal analysis acts basically as input to the for the structural analysis of a thermal as a thermal loading. So, thermal loading, that means this is the input as a thermal load for the structural analysis, then we do the stress analysis and we get the output as a in terms of the displacement, stress and strain field also. Now, this thermal loading means the completely temperature distribution, but in case of the transient analysis, so it is necessary to consider each and every time step what is the thermal data, thermal value, temperature distribution. So, therefore, we put all this temperature history to the stress analysis model. But to do this thing, thermal load is divided into the several load step. In this case, for example, the stress can be, if we assume that there is a heating phase and the cooling phase also. So, heating phase the temperature is increment during the welding process, and during cooling phase temperature decreases from the maximum temperatures to the room temperature value. So, we can divide this as a total thermal load. So, from during the heating phase and during the cooling phase also, this total thermal load, once we come back to this particular temperature, ambient temperature, we divide, this is the total thermal load, but during the analysis we have to make it the incremental way. So, we cannot put this total load as a single time step, and we may not get the, not able to get the temperature stress distribution as an output in a single step. Basically, this total thermal load, that means the maximum temperature to ambient temperature. So, we have to make this as a n number of division, that we consider this as a thermal load. This can be coincide with the temperature, that means the time step also within the, this is thermal load, and we divide this in terms of the total number of time steps, such that we will be able to capture after ending of the each time step what was the temperature value before and after. So, therefore, this total thermal load can be divided into number of steps, and it is possible to analyzing each and every step also. Once we getting the output as a stress displacement, stress, temperature for the one increment of the strain component. Then we keep on updating the next step by simply adding all this stress value, strain component value and displacement value. So, that is why in that way we normally progress the stress analysis model. So, therefore, thermal load is divided into several load steps and we analyze each and every load step. And then it is obvious that from the stiffness matrix with the stiffness matrix and along with the boundary conditions, and we calculate. So, this is the general form of the matrix, the solution. We normally form the K matrix, stiffness matrix, and delta is the displacement field that is defined each and every node point in a discretized domain. Then F is the load, and F is the load. In this case, maybe it is only we can consider the S as a thermal load in this particular situation in welding process, but this thermal load, but it can be added with the if there is any concentrated load or distributed load is there in particular problem also we can add this thing, but once we solve this equation, matrix equation, then we will be able to get the what is the displacement value. So, here the output is the displacement field. So, once the displacement field and displacement value each and every node point. So, once we get the displacement value each and every node point, then we convert to into other strain component we further calculate, and what is the increment of the stress, that is also we can calculate. So, apply load increment in the several load steps. Definitely first the division of the several load step is required and analysis of the each and every load step is required. So, single load step can be considered if all the elements are within elastic limit. It means that it is always incremental mode, but since within the elastic limit in actual process, actual mechanical analysis, in this case the one single load step. So, that means this kind of load step can be applied such that if we can ensure that all elements are within elastic limit. So, we can increase this can be considered as a single load step, and we can reach the analysis from directly this point, exactly the just up to the yield point. So, there we can get the stress distribution if it is within the elastic limit. Now, estimate the nodal displacement and convert it into the strain and stress components. So, once we getting the displacement field, then we convert into the strain components. For example, strain can be related to the strain displacement matrix B and strain displacement matrix in the displacement field. So, displacement field is known, then if we multiply this thing strain displacement matrix, then we will be able to get the what is the value of the strain distribution of this after the particular step. Similarly, stress can be estimated by either D into epsilon. D is the elasticity matrix. If the analysis is within the elastic limit, then we can do for the elastic we can use the value of the D, the elasticity matrix. If you remember, the elasticity matrix can be only associated with the different material properties. For example, it is associated mostly the Young's modulus and the Poisson's ratio. With that, D is accounting all the elements of the D is accounting this thing in the different form. So, therefore, D is the elasticity matrix. But if some elements goes into the plastic domain also, that means within the plastic, then in that cases we can estimate the stress value of this particular element considering the elastoplastic matrix DEP. So, therefore, depending upon whether the element is within the elastic zone or plastic zone, we can update the stress value by looking into the either D elasticity matrix or DEP elastoplastic matrix. We will show how the elastoplastic matrix can be formed also in the next slide. So, therefore, once we progress the analysis in this during the welding process, so it is also necessary that we have to check, because each and every load step, after the load step or the time step, we can get the effective stress value. So, we can get the effective stress value, that is the average stress or effective stress value, which is can be represented by following the von Mises yield function form. Okay, so, this in terms of the principal stress components. So, therefore, this value always we compare with respect to compare it with the yield stress value. That means whether this effective value is more than the yield stress value or less than the yield stress value. Accordingly, we can decide that whether yielding has happens or not, or if some elements can go below the yielding point and some elements go above the yield point. So, accordingly, we can use this D matrix or DEP matrix, or we can do some iterative calculation to make it the converged solution whether within the elastic limit or within the plastic limit. So, therefore, all the load step is applied in the incremental mode, that is already explained, because we first divide the number of load step has to be considered, then in the incremental way we apply the each and every load step. So, once all the load steps have been completed, then we will determine what is the plastic strain, stress, etc. value, and we will predict what is the residual stress, the existing stress even after cooling to the room temperature, that indicates the residual stress value or residual strain value also we can get the output from the analysis. Now, according to Prandtl-Ross flow rule, we have already seen that the flow rule also that plastic the sustainability of this plastic deformation even after yielding, that has to be use some kind of the flow rule also. The incremental plastic strain is proportional to the deviatoric stress. If we apply the flow rule also, in this case we consider the incremental plastic strain is proportional to the deviatoric stress component. From that point of view, we can reach some kind of the relation between the stress strain value. Now, at any particular load step, this is the incremental strain value, which consists of the both element elastic plastic and thermal strain. Now, what may be the, if you know this is the incremental strain value, so from the incremental strain value, what may be the incremental stress value? So, in a particular step. So, incremental stress value, once we estimate the this incremental strain, from there we can estimate the incremental stress value. Like that, if you see this is the elastic matrix and this is the plasticity matrix, dP, d elastic and d plastic, and then total strain minus of this is the elasticity matrix. I think D was already explained this thing, D is the elasticity matrix if we consider. So, DE here indicates the elasticity matrix. Now, from the elasticity matrix we estimate the thermal strain, but remember here we can see we are considering thermal strain as elastic strain. So, in this case thermal strain we estimate minus of thermal strain, because in this case the thermal strain is the input, and then from there this is the elastic, and finally we can say this can be considered as a D elastoplastic matrix, DEP, thing like that. So, therefore, D elasticity matrix, and in this case is ET represents the local slope of the stress versus plastic strain. So, local slope stress versus plastic strain, suppose this is the elastoplastic matrix. So, at this point this is the local strain, and at this point what is the slope, that indicates the ET. So, local slope of the stress versus plastic strain, or we can say the in this case the slope at particular point, and del F by del sigma, it indicates the deviatoric stress component. So, in these cases it indicates the deviatoric stress components, and F we can estimate the deviatoric stress component. In this cases F we assume the functional form. In these cases we can assume the functional form follow the von Mises yield functional form. So, from there we can estimate the del F by del in terms of the deviatoric stress component and other parameters associated with this thing. For example, here you can see G is the shear modulus also. So, therefore, this way we can see that d sigma can be represented that the increment of the stress is basically equal to the D matrix and the total strain and minus the thermal strain, that is the value. This is the increment of the stress value during this any incremental analysis. So, therefore, if we follow this, once we are considering this thing del F by delta deviatoric stress components, therefore, if we follow the functional from von Mises, there from there we are following in this expression comes from the von Mises yield criteria and Prandtl-Ross flow rule. From both the point, if we follow this thing, we can get the different functional form or some relation. For example, here we assume that incremental plastic strain is proportional to the corresponding deviatoric stress component. This assumption comes from this thing by following some Prandtl-Ross flow rule. From their point it is coming, and once we following the yield criteria, and that yield criteria should it's a functional form can be represented the von Mises yield functional form. So, therefore, if we estimate del F by it in terms of the deviatoric stress component as well as this value, average value of this is the yield point value, particular point. So, this yield point value, this yield value of a particular strain value. So, then this yield value can be considered depends on the strain hardening behavior of a particular material. So, this can be also updated of the strain hardening behavior. For example, if this particular strain value, this is strain component and this is stress. So, in this particular strain value, so we are getting, so this is the yield point. Now, this is the yield point. So, then here we are getting the sigma bar. Now, once we reach this point, we are considering the strain value at this point. So, in incremental strain reaches at this particular point, then this is the corresponding yield value, which is more than that of the sigma 1y. So, therefore, sigma 1 to sigma 2, when from this point to this point reaching this thing value, it depends on the strain hardening coefficient, the n value, the slope of this logarithm slope of the, if we follow the stress is relation the k epsilon to the power n. So, in the logarithm scale, n represents the slope of the this curve. So, therefore, that is why we know the strain hardening coefficient, and from there we can estimate we can define the different value of the yield point, which evolve following the isotropic hardening rule. So, finally, this for incremental load step, the final metric equation can form like that, the stiffness matrix dl, the incremental nodal displacement, you can say like that, and incremental equivalent nodal forces due to the thermal stress only, in these cases dl thermal stresses only, and dB is the incremental external force. In these cases we normally do not consider as not associated with the welding process. So, therefore, K dl equal to only the thermal load is there. So, if we solve this equation, then we will be able to know what is the displacement field, and already shown that once we get the displacement field even in incremental mode, then you need to consider convert in terms of the strain field, and from the strain field we can estimate what is the value of the stress field, and that is the overall analysis procedure in case of the mechanical model associated with the welding process. Now, solution strategy of stress analysis model. So, in these cases normally we follow, even in any standard commercial software, we normally follow the fully coupled thermomechanical analysis possible. So, in these cases fully coupled thermomechanical analysis means the stress analysis depends on the temperature distribution as well as the temperature distribution depends on the stress state. So, it is normally happens the temperature distribution, it is true that stress analysis depends on the temperature distribution, but in some point the temperature distribution also depends on the stress state. For example, in case of the high deformation process, so deformation process it will generate some amount of the heat generation will also be there. So, that means stress temperature distribution also affected by the stress state. In that cases it is necessary to consider the coupled thermomechanical analysis, but this thermo and mechanical analysis in these cases perform simultaneously. So, computational time is very high, but in other ways sequentially coupled thermomechanical analysis, in this cases the temperature field is predefined for the stress analysis. That means first we obtain the temperature analysis. So, once we get the temperature analysis, we consider all the data, then we perform the mechanical analysis. This is called the sequentially coupled analysis. In that cases this is more suitable in case of the welding process, because the other way also temperature distribution hardly depends on the stress analysis or stress state. So, that is why in particular to fission welding process we normally follow the sequentially coupled analysis. That means first we do the temperature analysis, after that we do the mechanical analysis. Flow diagram sequentially coupled thermomechanical analysis, something like that we follow even in standard commercial software also, we can see that how it works. So, physical model, the real world model, first is we define the full geometrical domain, that over which we are supposed to get the solution. Then in these cases, for example, laser welded joint, we define this is the dimension of the solution domain, and autogeneous welding process there is no material deposition. So, here you can see this is the actual domain. In case of the welding process. Now, we are representing this in the mathematical model of using the finite element method. So, then in the FE model, finite element model, we consider the half of the domain. For example, titanium alloy, half of the domain, because of the domain size of the domain depends on the symmetric nature of the problem itself. So, in these cases we consider the symmetric problem. So, therefore, it is not necessary to analyze the whole domain, but rather we can consider only the symmetric part. In this case we can consider the half of the plate also, and then we can do the analysis, but accordingly we have to define the symmetric boundary condition, and then in this case we can reduce the computational time during this process. So, once we convert the actual welding problem to in the domain of the FEM numerical model, if we convert it, and then we consider this is the domain of the mathematical analysis. Now, in these cases we need to define that material properties. So, first material property has to define, and it is possible both constant material properties as well as temperature dependent properties. It can be input can be given in the form of a tabulated form also. The data should be available, thermal properties, for example, this thing latent heat, then density, thermal conductivity, specific heat, all these values can be given. And apart from that, if we do for thermomechanical analysis, then mechanical properties should be given also, that Young's modulus, yield stress value, and then alpha, that means thermal expansion coefficient, then what is the plastic strain value. All these parameters of plastic strain value is required, because each and every plastic strain value, what is the value of the yield stress in the plastic domain. For example, if this is this kind of input is required also, Suppose this is the plastic. So, each and every, this is the strain and what is the corresponding value of the sigma y and what is the corresponding value. So, that kind of the value is required to given, because this experimental value as in because we already mentioned that things when we estimate the equivalent stress value from the theoretical analysis by assuming some kind of the plasticity model. From there we can convert this three principal stress in the form of a equivalent stress single value, and that single value always we compare with respect to this experimental value of the yield stress, and then if we from this comparison we can decide whether particular zone is in elastic domain or whether it is particular zone in plastic domain, and that is why it is necessary to define all these mechanical properties. So, now once it is defined all the properties, then thermal load. Thermal load means the thermal analysis has to be conform. In these cases we can use some heat source model, already explained this thing. The heat source model can be defined, it may be surface or it may be some volumetric heat source model. So, in this case we can consider double Elastoplastic heat source model, and then geometrical parameter, for example parametrical bed A, B, C, that means all related to the heat source parameter has to be defined, and we can use some user subroutine also, and such that we use some kind of the Fortran language to define that user subroutine, and we can define even in some commercial software also, and we can interact with the software by using user subroutine. So, we can develop, we can define all this model in the user subroutine, and then thermal load, and then after application of the thermal load, then boundary condition for heat transfer is required. So, in this cases the boundary condition for heat transfer, the film condition, that fusion zone heat conduction, that means heat transfer coefficient, thermal conductivity, that means which part is basically we are considering that there is a heat loss from the boundary, that has to be defined, which part is from the radiative heat transfer occurs on the surface boundary, the interaction on the surface has to be defined. So, once we define the all these properties, the thermal load and the boundary conditions, and then we can perform the this thing analysis. But before that, this is also necessary to give the mesh implementation, that means this thing we have to in the domain, this is the input to the software, and then this is the have to discretize the domain, then discretize the domain, that coupled temperature displacement value depending upon the analysis type, whether you want to do only the thermal analysis or whether you want to do the thermomechanical analysis. Accordingly you have to choose the type of the element. Then so once we type of the element, and also we can create the mesh, for example in near about the high temperature gradient zone, for example near about the fusion zone, we can create the very fine mesh also to capture the high temperature. There is a drastic change in the temperature also, we capture the temperature gradient there, and remaining part we can create the coarse mesh also to avoid the or to decrease the computational time. Then mesh generation, then mechanical boundary condition is also necessary to apply this thing, that here also you have to select the particular node point, which cases that we can assume the displacement becomes 0, and then in this case for example along edge, particular edge ux, uy and uz equal to 0. It means that one particular node, the displacement along x axis, displacement along y axis and displacement along z axis, all degrees of freedom are 0 in this particular position, and some cases also you can restrict only the 2 degrees of freedom, for example uy and uz 0, but there is a deep displacement may happen along the x axis. So, similar way also we can put all the boundary conditions. Now, in this case once we do the all this boundary condition mechanical, and history output can be getting the thermomechanical model in terms of the displacement field, stress, temperature and heat flux, all parameters are the output from this model. So, this way we can see that first in this case the model, all these things we can put that we can do the thermal analysis once it is done, and then we can start the mechanical analysis also. But before that we can choose the element in such a way that this should support the thermomechanical analysis. So, therefore, once you get all the thermal analysis, then after that the mechanical analysis can be done. So, like that it is called the sequentially coupled thermomechanical analysis, which is normally followed in case of the oiling process. So, visualization, once the analysis over, we can see the results also, that data selection inbuilt Fortran program is also there, extract the desired output for any point, maybe on a particular node point you want to get some information particular net, what is the value of some temperature or some information in the sense the temperature stress value or something like that. that is possible to get particular point, or finally we can get the temperature distribution. For example, this is temperature distribution, stress distribution, and the distribution of the distortion as an output, but some sort of data processing is required. So, residual stress distortion or stress analysis, basically that represents the residual stress, and color contour plot is possible, different color we can select, that contour plot, both are possible to get the output, and distribution of the stress patient with the transverse direction is also possible. That means not only the stress distribution, the whole domain, if you want to particular plane, we want to see what is the stress distribution, that is also possible in this particular case, or the if you want to use some kind of the commercial software in stress analysis model. So, this way we can see, generally we can see that welding process is mostly associated with the sequentially coupled thermomechanical analysis rather than fully coupled thermomechanical analysis, but in general fully coupled thermomechanical analysis the computational time is huge. Now, I come to this point that although we have discussing the what we can develop the model also, and what we can analysis, and from the particular commercial software what are the output we can get in terms of the temperature distribution, stress analysis and distortion field. Now, I come to this point, what is the residual stress, which may be important associated to the welding process, and one of the most important issue in a solidified weld structure, the level of the residual stress, because the life of the component depends on the what is the magnitude of the residual stress also. So, therefore, it is important to understand the residual stress generation during the fusion welding process. So, residual stress is the undesirable characteristics that remains within the body even after removal of its original cause. That means, from the if you remove the external force, thermal gradient, that means once which the comes back to the ambient temperature after solidification, and then some existing stress is there, and that is can be characterized as a residual stress in a particular welding process. Now, this residual stress distribution or residual stress according to the lecture can be of different type. For example, type 1, type 2 and type 3, in these 3 category ways we can categorize the residual stress. Type 1 basically long range or macroscopic stress due to the inelastic deformation. For example, simply if you look into the bending, rolling, laser shock peening in that particular manufacturing process, even welding process also, we can see that type 1 residual stress. That is macroscopic stress, and definitely that due to the inelastic deformation. But sometimes if we lower down the scale also, if we look what happens if we in micro scale also, then we can see the intergranular interaction as a result of the neighboring grain morphology. So, grain morphology can also be, and its orientation also induce some amount of the residual stress, and this can be viewed as a lower scale. For example, in case presence of the several phase change precipitate. So, in general, if you look into that microscopic scale, the several phase change and precipitate, that actually induce some amount of the residual stress, and that is considered as a type 2 residual stress. And type 3 also, even within the grain itself, even further lowering down the scale also within the grain, it is possible to see that within the individual grain there may be some amount of the stress generation, that is called the twinning. Because of the twinning and in presence of the dislocation, they actually generate the residual stress. But in effect, we normally look into graphically also, if we see that this type 1 residual stress, the magnitude is relatively higher, in this case the type 1, but type 2 also, this is the very localized position, that means this within this grain or the orientation of the grain or grain morphology that induce the amount of the stress, and that magnitude is in the lower scale. We can see this is the magnitude type 2, and type 3 further within one grain, presence of the dislocation and twinning, that induce some amount of the stress, that residual stress, the magnitude is very small also. Here you can see the magnitude is a little more in this thing, but here you can see it is a very small magnitude. So, that is why it consists of the all the 3 actual process, in the actual, if you want to look into the residual stress and in the different scale also, we can see that it consists of the type 1, type 2 and type 3 residual stress. And we will see, because normally we analyze in thermomechanical analysis, we are normally able to predict only the type 1 residual stress, but if you want to look into the type 2 and type 3, then we need to consider the microstructural morphologies or phase transformation effect, and can be incorporated in the residual stress analysis. And we will show that what we can incorporate the effect of the phase transformation, such that we will be able to capture, we will be able to know what is the type 2 and type 3 residual stress during the calculation of residual stress in fusion welding process. Residual stress evolution can be like that only thermal cycle we can see in the overall, this is the thermal cyclical temperature, non-uniform temperature distribution that induce the stress value, and at the same time some metallurgical changes also happen, and mechanical constant or load. Because of the mechanical or constant load, and that is the that kind of if you know simple thermomechanical analysis, the elastoplastic analysis, then we will be able to know that because of the mechanical load or mechanical constant, what is the amount of the stress generate, and that involved in the form of residual stress that we normally predict the by simply following the thermoelastoplastic analysis. In this case, if you remember, the total strain we consider the consist of the elastic part, elastic strain, plastic strain and thermal strain. These are the three, and from here elastic and plastic part, and then we normally accounting this thermal cycle as well as the mechanical load constant. From that part we if we develop apply the plasticity theory, if we do follow the thermoelastoplastic analysis, we will be able to get that the residual stress distribution on the macro scale. But during the temperature distribution, there are some metallurgical changes may also happen, and that the phase transformation may also happen, that precipitates may also happen, and then within the grain also after solidification there may be changes of the dislocation and twinning may form also. All this actually induce some micro scale or nano in the lower scale residual stress also, and that comes under the category of 2 and 3. But if you want to capture that thing, then we simply added the other strain component along with these things. If you want to introduce the effect of the this phase transformation effect or the into the stress analysis. So therefore, all actually this mainly this metallurgical model is the lattice strain modification and residual stress generation, as well as the it induce the distribution evolution, and we normally interested to know what is the amount of the residual stress and what is the residual distortion happens during the welding process. But residual stress can be of tensile and compressive both way also. It is possible the tensile residual stress promotes the brittle fracture, hot cracking, fatigue failure, but compressive residual stress actually reduces the buckling strength of the structure, but improves the fatigue life. So therefore, it is beneficial if it is possible to generate some kind of the compressive residual stress in a welded structure. In case of the uniformly heated and cooled structure, distortion can be minimized. But cooling or heating can be uniform, then distortion can be minimized. But if it is a non-uniform, that actually induce residual stress and distortion also. In that case, welding locally heats a component and the adjustment of the metal restrains that heated material, and this amounts the greater than the yield stress value something, causing the permanent deformation, distortion of the component. So therefore, this kind then it generates some amount of the residual stress and the distortion also. Therefore, if we put the restraint means simply clamping. If you follow the clamping also during the welding process, so the clamp can act as a restraint, and that actually minimize the residual distortion. But components without any external restraint are free from move or distort in the response of the stress from the welding process. Definitely, if we remove the any kind of the constant also, then it's free to move, then it minimize the residual stress amount in this particular process. So that means clamping forces induce some amount of the, although it reduce the distortion, but at the same time it induce some amount of the residual stress if we put the some mechanical constant along the in the boundary in a welded structure. Some idea about the measurement of the residual stress is also required, because in this case we will be able to capture the different values type of the residual stress also if you know the measurement techniques. In general, the non-destructive techniques normally follow the X-ray diffraction method for the measurement of the residual stress, but this method is only limited to measure the residual stress only on the surface. For example, only about the 0.05 millimeter depth we can measure the residual stress using the XRD method. And if we want to measure using the XRD method in the and along the depth direction also, in that cases it is necessary to remove layer by layer. For example, if we measure the on the surface, then we remove the particular layer, then after that next layer we can measure the residual stress. But in these cases the measurement may not be very accurate if we are not careful during the removal of the particular layer. But in that other way also, if you follow the Newton diffraction technique, then it is possible to measure the residual stress along the very high depth of penetration. So for example, up to depth of 30 centimeter it is possible to use the Newton diffraction technique. But all these cases this follow the simple principle, that is the Bragg's law, and in this case the theta is the scattering angle, d is the interplanar spacing, lambda is the wavelength of the electromagnetic radiation. So, since it is the interplanar spacing, all this thing interplanar spacing is basically associated with the nanoscale. It means that if we follow the XRD or Newton diffraction method or Bragg's law of diffraction to measure the residual stress, it is possible to capture what is happening within the grain scale also. So, grain scale means within the one grain, then we in this Newton diffraction or X-ray diffraction method is more accurate to measure even in the type 2 residual stress also, and that means at the lower scale also. But there are other techniques also, that is called the semi destructive or fully destructive techniques, and it use some kind of the mechanical methods. And mechanical methods in the sense that, for example, hole drilling method or contour method, slitting sectioning method, these are the typical methods that are normally used for the mechanical measurement of the residual stress. It's the basic principle is the stress relief. For example, the strain is calculated in the hole drilling method also, what is the stress relief capture, and the delta D is the measure that amount, and D is the along the depth direction, what is the distance travel. So, delta D by D is the simply measurement of the strain, and since it is a stress relief, and then once we measure the strain in this mechanical method, then we will try to link the strain into the amount of the stress, and that we normally follow the elastic limit. That means using the Young's modulus, we try to correlate this strain with the stress value. So, therefore, these methods are semi destructive, and if measurements are limited to only one point of the structure, that can be repaired easily, that is true also. But this semi destructive, for example, hole drilling method, there is a need to create some small hole on the surface to measure the residual stress, and this mechanical measurement techniques is not much accurate as compared to the XRD or Newton diffraction techniques. So, therefore, but that is why the mechanical measurement is very suitable if you want to capture only on the type 1 residual stress, then we can follow the any kind of the mechanical measurement technique of the residual stress. But factors affecting the distortion also. So, anyway, once we looking into the residual stress, distortion is also associated. In case of the uniformly heated and cooled material, it is in principle the distortion can be minimized. But welding locally heats the component, and the adjacent metal try to restrain that particular material, heated material, and this generates the residual stress, and that we call the yielding of the material and causing the permanent deformation of the component. What are the different factors affect this distortion also? That the same thing, what is responsible for the residual stress, the amount of the restraint. For example, if we clamping the different constant, the different position, if we increase the clamping force also or clamping points also during the welding process. So, therefore, amount of the restraint, this distortion depends. What are the welding procedure? For example, if we follow the arc welding process or laser welding process, definitely the distortion pattern and residual stress generation will be different. Then parent material properties, that means parent material properties, for example, in one cases we are doing the welding process is the high conductive material, other cases is the low conductive material. So, therefore, properties, and at the same time thermal expansion coefficients, there is a difference in thermal expansion coefficient among the different materials also. All these differences in the properties actually generates the different pattern or different value of the residual stress and distortion in a welded structure. And weld joint design, for example, whether it is bar joint, lap joint or T joint or any other, the gap between these two joints is very high. So, all these factors influence the amount of the distortion residual stress also. And part fit up, that means what we can fit up we can join preparation before the weld process also, that actually influence the amount of the distortion. Restraint to minimize distortion, that we have already seen these things. And of course, if we remove the components welded without any external resistance also are free to move distortion. That means if we remove this distortion, that is free to move, that actually minimize the residual stress. And therefore, clamping components, definitely it is very important in the residual stress also, the clamping part to correctly analyze the residual stress and distortion analysis, because this acts as a boundary condition during the welding process. Eliminating distortion, simply the two methods, the preset members to counteract the distortion. So, if you know the angular distortion after welding process, what will happen? Though if we pre-stress also before welding, that will help to reduce the element distortion in the simple way. The fixtures to the clamp workpiece in place, fixture can be made to clamp the workpiece in place. The restraint reduces the distortion, but increases the residual stress. That is true also. If we put too much of restraints, then that also reduces the distortion, but at the same time it increases the residual stress. Therefore, we need to optimize in the real situation and practical cases. And finally, if you want to reduce the residual stress and distortion, that some sort of heat treatment we normally follow after doing the after the welding process. That is the one of the most convenient way to relieve some amount of the residual stress relief through the heat treatment techniques. Other part also, reducing the residual stress can also be done, the selecting appropriate procedures, the welding sequence, that is also important, and what we can design the fixture also, all this important to reduce the residual stress, and selecting the best method for stress relieving and the removing the distortion. We will have to optimize the different process, also different techniques, different methods for the reducing the residual stress. Selecting the design, detail and the materials to minimize the effect of the residual stress. So, selecting the design of the particular weld joint as well as the choice of the material also influence, or the choice of the fixturing material also, that also influence the residual stress generation in case of the welding process. So, therefore, techniques to minimize distortion, that welding fixtures to physically distant parts, that is the one point. Heat sinks can be used to rapidly remove the heat, that also possible. That means we can use the high conductive material also and at the base plate on the fixture material, so that quickly conducted the heat. Tack welding, for a long welding we can put the tack before actual welding process, also create the rigid structure prior to the welding process, and this is the one most convenient way to simply preheating the material. So, if we preheat the material, that means before welding if we preheat the material, then in that case the temperature difference, temperature gradient can be reduced. So, therefore, generation of the residual stress distortion can be minimized, and of course, stress relief heat treatment can also be used in case of the welding process. So, here you can see some results also, the distortion in the microplasma welding process. If you see that in the microplasma arc welding process, we have used the, I think in this case we use the titanium alloy, and the 4 millimeter per second welding speed, and the current is the 11 ampere, and the thickness of the metal is I think 0.7 millimeter, 0.5 millimeter thickness sheet. So, here you can see the distortion pattern, the U3 distortion pattern are different in these two cases. So, why it is different? Because first cases it is done, there is stress analysis, stress and distortion analysis both. Here we are showing only the distortion pattern also, but in these cases we can use the small displacement theory, and the second case we can consider the large displacement theory. So, once we consider the large displacement theory, then it considers the very localized variation of the displacement. So, that is why it is able to predict if there is any bulk, any buckling is there or not. That kind of the phenomena is possible to consider if we consider the large displacement theory. So, that is why, although we have done the same process parameter, the distortion analysis, but the two cases the distortion pattern are different, but because one cases we have used the small displacement theory and large displacement theory. Definitely large displacement theory more intricate localized variation of the displacement changes. So, that is why we are getting the different pattern. Here some results of distortion and residual stress, we can see the residual equivalent displacement. So, that means residual equivalent displacement means that in this case the displacement field is there each and every node point, but we consider the magnitude of the displacement field equal to root over of u square plus v square by w square. That means the same component value magnitude of the each and every node point. There are 3 displacement field u, x, y and z component. We just making the magnitude of this thing. Then residual equivalent displacement. We can see that displacement becomes very high at the particular zone and low in the other point also. That kind of the prediction is possible if you can do the stress analysis, that means thermomechanical model. If thermomechanical analysis, here the residual equivalent strain. So, displacement can be predicted. At the same time, the equivalent residual displacement strain component can also be predicted from the analysis. So, here in the strain component, you can see at the middle the strain component is very high. So, around 0.15, the single value of this thing. So, temperature dependent material properties has been used. Bilinear isotopic hardening model is used in this particular analysis, and the linear laser welding process, the power equal to 4.5 kilowatt, speed 41.7 millimeter per second, and spot size was 63 millimeter, 0.63 millimeter. Similarly, some sort of analysis can also be explained this laser spot welding process, the power 1 kilowatt and on time 0.15 second. So, once on time 0.15 second laser was on for 15 second, then after the switch of the laser, then we can get this is the residual distortion, this is the equivalent distortion is confined in the very small zone also. Similarly, on time 0.65 seconds. So, laser was on up to 0.65 second, and then after the switch of the laser, and then we can get this is the distribution residual distortion, a particular point. So, this kind of the output, so in terms of the individual component also as well as the equivalent value, we will be able to get the as output from the analysis, thermomechanical analysis. In this case, thermoelastoplastic model, that means material behavior has been considered the elastoplastic material by linear isotopic hardening. Von Mises yield condition has been used and we followed the Pandel-Ross flow rule. From that point we are getting this kind of the residual distortion we can get. Similarly, for the these two cases we can use that in this case the 0.15 second on time power laser spot welding process, we can see the residual stress generation. Residual stress is confined with very small zone, and you can see the residual stress is maximum at this point, and this point is the maximum residual stress. You can see that this maximum residual stress, and this is the equivalent plastic strain. Also you can estimate this thing. Equivalent plastic strain is a very small value which is confined in the small zone in case of the spot welding process. So, it is very important to know that in this case the boundary condition is very important because it influences the level of the residual stress as well as the distortion. So, therefore, in actual welding process, what boundary condition we have followed the clamping condition, the similar can be represented by, like in this particular analysis, for example, here also you can put some constant value. Here also you can put some constant value depending upon the, and this side was the symmetric surface. Putting the proper appropriate boundary condition, we will be able to get this predict the accurately this residual stress and distortion field. So, that is all today. Thank you very much for your kind attention, and next part, the effect of the phase transformation effect, what we can on residual stress analysis, that we will discuss in the next part. Thank you.